fine. That's fine. So like I said, because you've heard this yesterday, I hope to zip through this really quickly. So if I gloss over something, then and it's still unclear to you, then just stop me. That's fine. Okay. Now, recall that in motion so far, right, when you've got like a drawing that demonstrates how something's moving, something like this, right? Even though it's a two-dimensional diagram, so far in motion, it's actually been a one-dimensional situation, right? So you've got something and it's moving up and down, and that's your displacement, right? And your horizontal axis is not really horizontal. It's actually time progressing, right? It's like snapshots of the same thing going up and down, okay? But now we are like really actually going into two dimensions. So x goes back to its spot on the horizontal axis and y goes up there, okay? So x is returning back to being a horizontal thing, and we have to introduce a second variable. Okay, now therefore, when you're talking about things in two dimensions, right, in two-dimensional space, you've got a couple of alternatives when it comes to describing something in two-dimensional space. Okay, so I want you to think back to the unit circle. Remember that? Actually, not the unit circle, just a circle. Okay? Because when you're describing a point on the circle, okay, you can describe it in two ways. I mean, the obvious way for you guys is to use Cartesian coordinates, right? X's and Y's. Okay. So for instance, you might call that, say, I don't know, 4, 2 or something like that. Okay. So that gives you horizontal and vertical definition for where it is. Okay. But that's not the only way. You can also use polar coordinates, right? And coordinates is kind of a funny way to think about it, but the coordinates just means two things that are matched up together, and you've got an angle, and you've got the distance to get there, so it'd be r in this case, right? So therefore, you've got exactly the same two ways of describing projectile motion and an object which is moving through space, okay? So here are two definitions, right? Your Cartesian definition, and you've got your polar definition. Now, they don't always get called this, but I hope you can see the parallel. We'll do the polar definition first, right? You need two things. You need an angle, right? Angle of inclination. And because we're talking about, rather than something's position, we're talking about its motion, okay? You're going to need an angle, and you're going to need a velocity. Okay? Now, properly speaking, velocity here actually might as well be speed. Because when we're talking about projectile motion, things aren't going to go back and forth. They're just going to go. And they're always actually going in a forward motion. Okay? Now, the Cartesian definition is what happens after you get the rectangle out and you resolve your velocity. Do you remember that? Just ring your bell. Nod slowly. Yes? Okay, good. So you've got your x dot and your y dot, right? Corresponding to your horizontal and your vertical momentum. Okay? Now, these two definitions, they overlap. They're just like these two overlap, okay? You can describe any point in either of those ways, okay? So let's try and review, how do you change between them? How do you convert? Or if you're going from a polar definition to a Cartesian one, how do you resolve it, okay? So that rectangle again. So let's think about something that's been propelled upward, and maybe you guys can help me here. Suppose we know that it was propelled, let's go with a polar definition here. It's propelled up at an angle of 60 degrees, okay? And let's fire it off at, say, I don't know, 120 meters a second. Right? So there's our polar definition. I've got an angle, I've got a velocity. How do I go about resolving it? I'm gonna need to relate. This is my v, right? And this is you can call it alpha or theta if you like. Okay. The vertical and the horizontal bits that I'm after, right, correspond to this distance across here and this distance up here, right? So it's just straight trig even in right-angled triangles, right? So with this 60 in place here, there's my 90. For example, to get x, I've got, this is the adjacent sides of the angle, and this is the hypotenuse, right? So which trig ratio am I going to use? Cos, right? Because it's adjacent to hypotenuse. So I can say cos 60 is equal to x dot on 120, right? So obviously, if we're after the horizontal velocity, we just move that over. Cos 60 is a half. So there's our horizontal velocity, right? And you can recognize from here, right, you should have been given that set of standard equations. For x dot, this is, that 120 comes from the velocity, right? So that's v. And this a half comes from the cos 60. So that's where your v cos theta comes from. Okay? Yeah, ringing bells. Do the same thing for your vertical momentum. So I've got, instead of cos, I'm going to do sine, because that'll give me the opposite side, right? So that's y dot on 120. So exactly the same. I'll just rearrange this. 120 and sine 60 is root 3 on 2, right? Okay, now just pause for a minute. Root 3, right? It's about 1.7, thereabouts, okay? And this is your v sine theta, by the way. So this is 60 times 1.7, this is 60. So your vertical velocity is more than 50% bigger than your horizontal velocity. Does that make sense? Does that kind of match up with what you'd expect? Yeah? Because, you know, you're firing at a very high angle, okay? What angle would you have to fire it at for your horizontal and your vertical velocity to be the same? 45 degrees, right? Okay, good. So that's fine. Obviously, if you wanted to go in the other direction, let me draw another one over here. If what you were given was your horizontal and vertical velocity, okay, let's go with, say, 5 meters per second. There's your x dot, and 12 meters per second. There's my y dot. Okay, how do I go in reverse? Well, the things I need are this angle and this length, right? So you can get the length by using Pythagoras, okay? And that's where this other important equation comes from. Velocity is x dot squared plus y dot squared, okay? So therefore velocity, I'll just take the square root. So what would you get here? Well, because I picked nice numbers, so you can get 13 meters per second. Yes? Theta. How do I get theta? Yeah, so I've got opposite and adjacent, right? So tan theta, sorry, I've already written theta. That's going to be y dot on x dot, rise over run, okay? So in this case, my actual theta would be tan inverse of whatever that is, okay? So, you happy with that as a review? You're going to need to have 1, 2, 3, 4, these kinds of equations, right? You've got to remember them, but they're pretty simple, to be honest. Now, there's a couple of things I want to add on to this. To make it projectile motion, this is just for things that are moving through the air and understanding how do we describe how they're moving, okay? Projectile motion, you know two initial conditions, actually two conditions throughout, about the acceleration of your objects. This is all about velocity, right? So do you remember them? If something's just been propelled and you're not putting any more force behind it, it's not like, it doesn't have a rocket attached to it or anything like that, and you're in a place of gravity, okay? What are the two acceleration equations that you get?
The acceleration in the horizontal is 0.
Good.
And the vertical is -g.
Good. Okay, now, these are actually your two starting points every time you start a projectile motion question, okay? You always begin from here and then you integrate up to get the rest of, you know, your bits and pieces and your actual equations of motion for that specific question.